All right, before I jump into today's lesson, does anybody have any questions? Anything y'all want to go over?
I already asked you, so
You got it? All right. Awesome. What's up, man? You have any questions you want to go over?
Excuse me, I'm turning on the mic.
All right. Yeah. Mhm. All right. You got a question you want to go over? Oh, go ahead. Yeah.
Is this the updated version?
Yeah, that's the updated version.
I see my name.
Yeah. Oh yeah, you gotta come check this out. I got you now. Yeah. Yeah.
And she
Yeah. Yeah.
Thank you.
No, but your name wasn't there before. Yeah. I got you now. Yeah. Yeah, yeah. Some services. I'm gonna say 5. Yeah. I mean, if you want to go and come back, I'm recording it, so yeah. So go there and come back. Yeah. It's in the book pickup is in Roscoe Brown, the ID office. Yeah. All right. Y'all good? All right, let's jump into it then. So there's a part of it that I didn't get to finish teaching, so we're finishing that up today. Yeah. All right, no problem, no problem. You're welcome. So yeah. Yeah, it just occurred to me I haven't done a commercial break for y'all in a minute. Hold up. Let me see if I got anything interesting I could tell y'all about. Like I ain't tell y'all about yet. All right, so I'm gonna tell y'all about this, but I personally can't make it. But if y'all can, like this will be fire. Real quick. Little commercial break. I mean, y'all also remember pantry next week, Wednesday and Thursday, get your groceries, right? No classes on Thursday, no class Monday, no class Tuesday. Um, what else? If you guys ever want like a free meal, they got them in Low Hall on the 4th floor. Get your free frozen meal for the day. Um, so here, there's this. Okay. Whew. All right. So they have a board game night on campus. I don't know if anybody likes to play board games, chess, checkers, cards, 21. Okay. So it's in the library on the 2nd floor, right? These are the dates. They got Monday, February 9th, Monday, February 23rd, Monday, March 9th, Monday, March 23rd, right? From 5 to 6:30. So like basically like right after class, y'all can go there and chill out for like a couple minutes if y'all want, you know. Like if y'all like chess experts, y'all could just go in there, 3 moves and y'all good, you know? So yeah, like there's that. And I don't know if I have anything else. I think that's it. That's a good question. There should be one for this semester, but I'm not sure. I haven't heard anything. Yeah. But that's a really, really good question. As soon as I hear something, I'm gonna let you know, I promise. Let me see if I have any other commercial breaks that I could tell y'all about. All right. Let's survey the class. This is just for the ladies. Um, I feel like there's some people in here over 25. Right? Y'all over 25? All right, we good. 2 year, first six credits, blah blah blah. All right, hold up. Good. Yeah, so I will get that video to you guys from last class, but let's get into this. All right, so we're just picking up where we left off, right? So now you guys have the histogram drawn, right? But the histogram can look in a couple of different ways, and that's what we're going to talk about right now. So histogram and relative frequency histogram. So make a histogram and a relative frequency histogram with 6 bars for the data in the table, right? And then we're going to show some ways that this could look. All right. Bless you. So just to recap, the histograms that we did last time, I'm not going to redo them, but more or less, this is what we came up with, right? This is like a prettier version of what we came up with. All right. So remember again for our histogram for the people that were commuting, right? Remember we had the 60 people and we were looking at how far their commute was from home to work, right? This was the histogram that we came up with, right? Remember that for our frequency, we can choose our axis however we want to do it. In this picture, they went by sixes. When we did it, we went by threes, right? And then these are the bars right here. Me personally, I like it if you guys put some type of design in each bar just to distinguish the bar from one another. For me, the design that I chose was to write the level that the bar was at, like the number, like this one was 12, this one was 21, etc. Right? But feel free. You guys can draw hearts and them, different hearts or whatever, like whatever y'all want, right? Just to distinguish one bar from the other, right? Going to the right a little bit, right? This is our relative frequency histogram. Remember, I was telling you that with the relative frequency histogram, they have the same class boundaries, right? The same x-axis. What's changing is the y-axis, right? So for relative frequency, you see how we have these fractions here, 0 0.1, 0 0.2, right? So this histogram is actually really, really tiny. It's really small compared to the regular histogram, which is at a whole number, right? But notice they look the same, right? They look the exact same. The only difference, like I was telling you, this is 6 over here, right? This is 0 0.10. 0 0.10 is just 6 divided by 60. Same thing, right? All right, so anyway, each bar is the corresponding relative frequency. Notice that the basic shape of these graphs are the same. The only difference involves the vertical axis. The vertical axis, y-axis, of the histogram shows frequencies, whereas that for the relative frequency histogram shows relative frequencies. All right. So that's like kind of just a cap of what we did last class. And let's move on to the distribution shapes. All right. So with this information, you should be able to complete your homework that's been posted.
Say something about the lab,
Yeah. That's what we're going to get into right now. You know, so distribution shapes, right? So histograms are valuable and useful tools if the raw data came from a random sample of population values, right? Hold on, let me just make sure something. Good, make sure the audio's on, all right? If the raw data came from a random sample of population values, the histogram constructed from the sample values should have a distribution shape that is reasonably similar to that of the population. Several terms are commonly used to describe histograms and their associated population distributions. So that's what we're going to go over right now. First thing we're going to go over is called mound shape symmetrical, right? So this term refers to a mound-shaped histogram in which both sides, more or less, the same, right, are the same when the graph is folded vertically down the middle, right? So this next figure is going to show you what a typical mound-shaped symmetric histogram looks like. So let me get that for you. All right. It may not look pretty. Like it's not going to be like completely the same on the left and the right, but for the most part, it looks like it is. That's what we're going for here. The look. It looks like it is. So here you go. This is a typical mound-shaped symmetrical histogram right here, right? So if I was to say fold this in half, right down the middle right here, the left side would more or less be the same as the right side. That's what I'm trying to say. This is called mound-shaped symmetrical. All right. Questions on it? Good.
Mark, can you do any example?
Yeah, we're working off the examples that we did for. Yeah. I got you. So the next one I'm going to talk about is called uniform. All right. For homework, they're going to give you like pictures, same pictures that I'm showing y'all here, and ask you, what is this? You know? Like, so all you have to do is identify what it is. So look, this is uniform, all right, or rectangular, right? So these terms refer to a histogram in which every class has equal frequency from the point of view. A uniform distribution is symmetric with the added property that the bars are all the same height, right? And then this figure is going to show you that, right? So this is uniform or rectangular, right? Every class has the same value, right? Like for example, let's say that there's 5 people in each class, five, like that, right? This is uniform or rectangular. Again, in practice, it might not be as pretty as this, but we're going for the look here, right? It looks like this. Yeah. It'll be uniform, but like for example, one they might not be even, you know? Like, all right, like let's say this bar might be just a little bit higher, and this bar might be just a little bit lower, that kind of thing, right? Like it might be jagged. That's what I'm trying to say. But for the most part, when you look at it, you could just say like, all right, this is definitely uniform. Like more or less, there's about the same number of items, people, whatever in each class. Yeah. Yeah. Right. So imagine that the textbook is showing you something perfect, like a perfect uniform, right? But in real life, that doesn't happen. There's variability amongst it, right? I'm more going for what does it look like? It looks to be uniform. Like some classes might have one or more people or less, but for the most part, it's level, you know? Mhm. You know, it's just a look. Yeah, just a look. Yeah. Mhm. Oh, what?
No, okay.
I got you. Got you. Yeah. All right, this next one is what you were asking about. Right? So we have another type called skewed left or skewed right. So these terms refer to a histogram in which one tail is stretched out longer than the other. The direction of skewness is on the side of the longer tail. So if the longer tail is on the left, we say the histogram is skewed to the left, right? And this figure shows that, right? Which shows a typical histogram skewed to the left and another skewed to the right. All right, so when you have a histogram that looks like this, wherever the tail is, that's the skewness, right? So this is skewed to the left because the tail of this is to the left. Over here, this one is skewed to the right because the tail is on the right. And that's it. Again, I'm just going for the look, right? This is what it looks like. All right. All right, this next one that I'm going to talk about, this is called bimodal. So this term refers to a histogram in which two classes with the largest frequencies are separated by at least one class. The top two frequencies of these classes may have slightly different values. This type of situation sometimes indicates that we are sampling from two different populations, right? And this is what a bimodal will look like. I'll show you guys right now. So here's what a bimodal looks like, right? So you see how there's twin peaks, right? There's two high points here, right? It's like the data begins to rise, it gets to a peak, then it just drops, then it gets to another peak, and then it drops off, right? That's bimodal. There's like two humps, all right? So basically for your homework, they're gonna show you a picture, right? It's gonna look something like this, and you just have to identify it. You know, like, oh, that's two humps, boom, that's bimodal. Oh, that's symmetric. The left and the right look the same. That's mound shaped symmetric. Oh, it's skewed to the left, the tail is on the left, or it's skewed to the right, the tail is on the right. Or maybe it's uniform, everything is the same. Right? You're just gonna identify the picture. All right, that should be simple. Yeah, sure. For bimodal, you want to see the definition? There you go. Go down? Okay, okay. So I want to elaborate a little bit on bimodal. This is just to be a little bit more clear on how this can happen, right? So a bimodal distribution shape might indicate that the data are from two different populations. For instance, a histogram showing the heights of a random sample of adults is likely to be bimodal because there's two populations, right? There's males and females, right? They were combined as one. If there are gaps in the histogram between the bars at either end of the graph, the data set might include outliers. All right. So let's talk about what an outlier is. So an outlier in a data set are the data values that are very much different from other measurements in the data set. For example, let's imagine that we're working at a company, right? And then the company has a CEO, right? The CEO is making millions of dollars, right? Whereas the individual workers, they're making like, let's say, minimum wage. So when someone asks the question like, oh, what is the average salary, or the median salary here at the company, right? That answer might be skewed a little bit. It might be higher than what the actual answer is because of the CEO salary. Everybody else is making like what 30,000 a year, but the CEO is making 20 million a year. So because of the CEO salary, that might push it up a little bit further, like a little bit higher than what it actually is, right? That's an outlier, for example. And it works in both ways, right? It can be a number that's too small or a number that's way too big compared to the rest. So outliers may indicate data recording errors. Valid outliers may be so unusual that they should be examined separately from the rest of the data. For instance, in a study of salaries of employees at one company, the chief CEO's salary may be so high and unique for the company that it should be considered separately from the other salaries. Decisions about outliers that are not recording errors need to be made by people familiar with both field and the purpose of the study. All right. So there's that. All right. So what do histograms and relative frequency histograms tell us? Histograms and relative frequency histograms show us how the data are distributed. By looking at such graphs, we can tell if the data distribution is more symmetric, skewed, or bimodal. If there are possible outliers, which data intervals contain the most data, and how the spread out of the data are, right? How spread out the data are. In the next chapter, we will look at measures of central and spread of data. Histograms help us to visualize such measures. All right. All right. Let's talk about one last thing. Cumulative frequency tables and ogives. All right. Sometimes we want to study cumulative totals instead of frequencies. Cumulative frequencies tell us how many data values are smaller than an upper class boundary. Once we have a frequency table, it is a fairly straightforward matter to add a column of cumulative frequencies. So the cumulative frequency for a class is the sum of the frequencies for that class and all previous classes. All right. So I'm going to tell y'all how to do it real quick. So this is a separate type of graph. All right, so here's your procedure. All right. So this is how to make an ogive. All right. First, you want to make a frequency table showing the class boundaries and the cumulative frequencies. All right. Step 2, for each class, you're going to make a dot over the upper class boundary at the height of the cumulative class frequency. The coordinates of the dots are upper class boundary, cumulative frequency class, right? Think of that as X and Y, right? Connect these dots with a line segment by convention, right? An ogive begins on the horizontal axis, on the x-axis, at the lower class boundary of the first class. All right. Let's look at an example. I'm sorry. I'm gonna show you. I'm gonna show you. It's a different type of graph. It's kind of like a line graph. Well, but you're gonna see it. So cumulative frequency table and ogive, right? Here's an example. Aspen, Colorado is a world famous, ski area. If the daily high temperature is above 40 degrees, the surface of the snow tends to melt. it then freezes again at night, right? This can result in a snow crust that is icy. It also can increase avalanche dangers. So this table gives us a summary of daily high temperatures in Aspen during the peak 151-day ski season. All right. So we have our class boundaries, right? So this is between 10.5 degrees to 20.5 degrees, 20.5 degrees to 30 degrees, et cetera, et cetera, et cetera. The frequency, this is the count of how many days was in that range, right? Remember that from last class. It's the same thing, the same table, right? But here's what's different. The cumulative frequency, that's different, right? Right. So the other stuff is still there too, but now we're adding another column, a final column. This is called a cumulative frequency. So here's how you do it, right? You look at your frequency table, right? Here's my frequency table right here. You start with the lowest class, like the first class, right? Boom, there's 23 people in the first class, right? Or 23 days, excuse me, in the first class, right? And then what you want to do is you want to add the next class frequency to it, right? So 23 plus 43 is 66. Then you want to add the next class frequency to that, right? So I'm going to take the 66, I'm going to add the next one, which is 51, to get the 117. So on and so forth until I get to my last class, right? Which should be the total of everything. In this case is 151, right? This is cumulative frequency. This is how you do it. Questions on this?
The relative frequency would be like the sum of all the frequencies.
You divide each one by the sum. Yeah. Or not, let me not say the sum. You divide each frequency by the total of everything. Yeah. This one you're just adding. You're adding the next class's frequency to the previous, right? And you just keep doing that until the last one should be the sum of everything, the total of everything. All right. But now what I want to show you guys is a different way to graph this. All right. So first I want to talk about it, then I'll show you guys. So this table is not crazy hard to do. This is just the addition onto the previous table that we did before. All right. The story for this is a little different though. It's not the same story. All right, so the cumulative frequency for a class is computed by adding the frequency of that class to the frequency of the previous class, as seen in the table, right? To draw the corresponding ogive, right, we place a dot at the cumulative frequency 0 on the lower class boundary of the first class. Then we place dots over the upper class boundaries at the height of the cumulative frequency of cumulative class frequency for the corresponding class. Finally, we connect the dots. This next figure is going to show you the corresponding ogive. Looking at the ogive, estimate the total number of days with a high temperature lower than or equal to 40. All right. Hey, how you doing, man? So let's take a look at that real quick. Excuse me. Hey, I got you. You want to see this table? Got you. So this is the ogive right here. Wait, go down or something. Good. You got it? All right. So this is the ogive right here. All right. So first, we start off with our lower limit, right? Which was 10.5. I mean, excuse me, my lower class boundary, right? 10.5. You're going to start off at 0. And then for the first class, it was at 23, right? And the upper bound of the first class was 20.5. right? Then the upper bound of the second class is 30.5, and that's going to be 66. Next upper class, excuse me, the next upper boundary is 40.5, and that's going to be at 117. So on and so forth, right? After you get these dots on the graph, you connect them by a line, right? So this is a line graph, right? And this is an ogive. Questions on it? All right. If you're wondering where the 23 to 66 came from, that's from the column for the cumulative frequency. I'm just putting those there. All right. And then that's it. So what does an ogive tell us, right? An ogive, also known as a cumulative frequency diagram, tells us how many data are less than the indicated value on the horizontal axis, right? So how slow also tells us how slow or rapidly the data values accumulate over the range of data. So what they're trying to say is that like you could tell how fast it's increasing or whatever by the steepness of the line, right? The more upper angle it is, the faster it's going, the more like kind of horizontal it is, the slower that it's going, right? I believe they asked us to do something though, right? They want to know how many days are where it was a temperature lower than 40.5 to 40 degrees, right? So you see right here, this is 40.5, all right? So how many days were lower than 40 degrees? It's right here, it's 117. Not bad, right? You just kind of look at it and you match it.
How many, what is the question? How
So
many?
the question over here was looking at the ogive, estimate the total number of days with a high temperature lower than or equal to 40 degrees Fahrenheit, right? So we have 40.5 degrees, right? So how many days were equal to or lower than that? 117. And that's it. Right? Because remember, it's cumulative, just keep adding it up. What happened? This part? Oh, the yellow? Got you. Yeah. All right, so in addition, the vertical scale can be changed to cumulative percentages by dividing the cumulative frequencies by the total number of data. Then we can tell what percentage of the data are below the specified value on the horizontal axis. All right. Questions on the OJA?
I don't understand on,
What you don't understand about it? Mhm.
uh, how,
How to do it?
yeah,
The table or the graph?
he resolves the question. Why 17? Why is 117?
So that's from the cumulative table over here, right? This is the 117. Remember, we started off with our first class frequency, which is 23. We add the next class to it to get 66, and we add the next class to that, etc. Right? So the question that was asked, right, is how many days, right, was the temperature equal to 40 degrees or less, right? So right there, we're talking about a third class, and the cumulative for the third class is 117. That's why, you know. But we'd rather you use the table to tell that, you know? Like the graph just makes more sense than looking at a table of numbers, you know? Yeah. And that's it. It's no drive. A line graph. That's it. Yeah. Try the homework.
Yeah. I will.
You guys have enough information to finish it. Um, bear with me 1 second. Let me Let me check how the homework's going for everybody. Okay.
When did I start career?
Career what?
Like, more, like the course, more for each, like career.
When you go to career services, that's when they do that stuff.
Next semester?
It could be next semester, yeah.
Okay, some classes like, okay, gosh. That's,
Oh, you mean like your major classes you're asking
yeah, like
about?
major.
Yeah.
The question, yeah.
Yeah.
When start the major classes, yes.
Yeah. Some people could start now, some people have to wait till after this classes start.
Because, yeah,
You know,
some people, they,
yeah.
like, I know it there, who she started now because she come here with grades from, she's transferred from another college.
Right.
So she is taking major classes.
Got
already.
you.
Yeah, she is started.
Got you.
Who has major classes here? Nobody.
Not many people would have them though.
Nobody here is taking major classes. Yeah,
Some people they have to finish their prerequisites before they can start into a major
I
class.
started
You know?
home, so I
Yeah.
don't have major classes there.
But you
It
will.
takes me to.
You will though.
That.
You could do that too. Yeah, that's an option as well.
What?
Yeah. You could leave this class for last. Some depending on the major. Some majors could do that.
I can leave,
Like this class for last. You know?
really?
Yeah. So depending on the major, some majors can do that.
3 minute office can,
They could. Yeah.
like now I can do the exchange, can I exchange now?
No, too late.
It's too late, so
Yeah.
oh wow,
Yeah.
so I can.
But when you were talking to your
next
advisor, you
semester,
could have no after next you're gonna pass this, so you won't need this again. You're good to go. Yeah.
I'm free too,
Yeah.
so I just need to go to where admission registration, where.
It's your advisor, and then your advisor will plan it out for you.
Request me an advice, hey, I want to start my major classes.
Yeah.
And
But that's not right now. That's in April.
on April.
April,
okay.
yeah.
March, April.
Right.
I have to wait until April.
Yeah.
Request to my advisor.
Right.
Let to know here.
Yeah.
Yeah.
Yeah. Yeah, I was just about to talk about that right now. Yeah, I got you. Yeah. All right, let's finish up a one last topic, right? This is really simple. All right. So we're gonna be talking about radicals. All right, radical expressions. All right. So in this section, we will establish some conventions about how we will treat the types of irrational numbers that arise in solving quadratic equations. In particular, we will develop a way of writing square roots symbolically. We already saw in the previous section that the solution to the equation x squared equals a are irrational numbers where whenever a is a whole number that is not a perfect square. In that discussion, we saw that solutions to this simple type of quadratic equation is closely related to the notation of a square root, which we treated in chapter 1 as an operation. One way to treat irrational square roots would be to agree in advance that we will estimate them to a given decimal accuracy. For example, if we agree to estimate square roots to 8 decimal places, a calculator might tell us that the square root of 5, right, which is given by square root 5, is equal to 2.236066798. If, on the other hand, we agree to estimate it to 12 decimal places, we would write square root of 5 is similar to 2.236067977,500, right? So we are going to handle irrational square roots in a different way, right? Instead of estimating, which depends in practice on using a calculator, we will adopt a symbolic approach, all right? So we're gonna make it a little bit simpler, a little bit simpler. All right. So I believe this was the new homework that was posted today. But it's really, really simple, I promise. Really, really simple. All right. So the square root as a symbol, for any non-negative number k, the symbol square root k is the square root of k represents the non-negative solution to the equation x squared is equal to k. Said in another way, the symbol square root k represents the non-negative number which satisfies the square root of k squared, which is equal to k. It is worth pointing out, right, what is new about this definition in our, let me continue. So in our previous understanding of square roots, all right? So square root k actually consists of two separate symbols, k representing a number and the radical sign, right? That little house thing, excuse me, which represented an operation performed on the number k. In our new definition, by contrast, the square root of k represents one symbol with two parts, the radical sign and the radicand, what's inside of the radical, right? As the quantity k inside the radical sign is known. Keep in mind from the introductory section that the equation x squared equals k typically has two solutions. Excuse me. One positive and one negative. In this case, the square root of k represents the positive solution, all right? From the point of view of solving quadratic equations, at least for simple ones, this definition in a certain case cheats. We have defined the symbol square root of k to be the non-negative solution of x squared is equal to k. The other solution will then be its opposite, written as negative square root of k. The following examples illustrate this point. In fact, we can write this as our first strategy for solving quadratic equations, all right? So, here's the first strategy. The first strategy is to solve a quadratic equation of the form x squared is equal to k. An equation having the form x squared is equal to k has two solutions written symbolically as square root of k and negative square root of k. For now, we'll be applying this strategy when k represents a non-negative number, right? In the next section, we will consider what happens when k is negative. Notice that in the special case, x squared is equal to 0, the two solutions is square root of 0 and negative square root of 0 are the same. They are both 0, but rather than thinking of this as a special case of a quadratic equation with only one solution, it is more convenient to think of this as a quadratic equation with two solutions that just happen to be the same. All right. All right, let's jump into some examples. We're going to start off basic, and then we're going to build it up. So here we go. So we want to solve these quadratic equations right here, right? So for the first one, right, for A, I have x squared is equal to 7. To solve this, I want to solve for x, right? So I want to get rid of the square root. So how do I undo a square root? Excuse me, I want to get rid of the square. So how do I undo the square? I use the square root, right? That's how I get rid of the square. But what I do to one side of the equation, I have to do to the other side of the equation, right? But I'm telling you, here's the trick. When you do this to the other side, it's going to come out with two answers, one positive, one negative. So your answer literally is x is equal to negative square root 7 and x is equal to positive square root 7. Right? If this is web work, you would enter this in and separate, you would enter in both answers, but separated by a comma. Right? So it would be like negative square root 7, comma, square root 7. That'll be the answer in web work. All right? Your homework. That's what I mean, right? Let's try the next one. The next one I see is B, right? So this is x squared is equal to
No,
129, right?
yeah.
So tell me, how am I going to answer this, somebody? What am I going to do? Literally the same thing as the top. Right? I'm going to square root both sides, right? And this gets rid of the square. So what are my answers? I'm going to have two answers.
How I call that? I'm sorry. Look.
Square root, the house. Square root.
Square root.
Square root.
Okay.
So what are my two answers? Good. Negative square root 129 and positive square root 129. That's it. Questions on this? All right, let's try C. C is a little bit harder. This is x squared equals to 15. What should I do?
That's for equal or
Square root each side, right? This is positive and minus. So now what are my two answers? X equals negative square root 15 and positive square root 15. And that's it. All right. Questions on this? Good. Yeah. I'm building up to it though. That's more advanced, that question. All right. So the point of these simple examples is not really to show how to solve a quadratic equation, although we have technically done so. The point is to illustrate the fact that we have used a symbol to represent a solution to an equation. It has the advantage of needing no estimation. For example, the square root of 129 is a symbol representing the exact value of the positive solution to x squared is equal to 129. It has a disadvantage, however, of hiding the fact that the symbol square root of 129 is a symbol for an actual irrational number whose value is approximately 11.35781691600547221, etc. All right. There is another more serious disadvantage to the symbolic approach. If we get too excited about the new notation, we would be tempted to say that the solution of the quadratic equation x squared is equal to 9 is equal to the square root of 9 and negative square root of 9, right? And done. This seems like a wrong way to answer the question when it is much more easily understood to say that the solutions are 3 and -3. Unlike the examples above, 9 is a perfect square. And so there is no need to have a special notation made specifically to address the irrational numbers. All right. For these and other related reasons, we're going to agree to a series of rules about how to write square roots symbolically. These rules have evolved over the course of history and are generally accepted. All right, so here we go. All right, rules are simple. All right, simplified square root notation. So the symbol, the square root of k, is called simplified if the following conditions hold. The radicand k has no perfect square factors, and 2, the radicand k contains no fractions. All right. So what's underneath the square root cannot be a fraction, and it cannot have no perfect squares. All right. In addition, any expression containing radicals must satisfy a third condition. No radical expression shall appear in a denominator. It's illegal to have radicals in our denominator, period. All right. Those are the rules. It's illegal to have radicals in our denominator. Right? Right. Like it can't be like 1 divided by the square root of 2. That's illegal. Yeah. That's fine because square root of 9 is right, which is just 3. Yeah. But you could just say 1/3. Right? So what happens if we encounter a radical expression which is not simplified? We will take the effort to simplify it, rewriting it in an equivalent form, which is simplified according to the conditions above. In order to do this, we will rely on 2 basic properties of square roots. So here they are. 1 second. All right. So some properties of square roots. If a and b represent non-negative numbers, then the square root of a times b is equal to the square root of a times the square root of b. And also the square root of a divided by b is equal to the square root of a divided by the square root of b. All right? These are special rules. All right? Should you guys memorize this?
Yeah.
I don't hear no answer. Should you guys memorize this? No. Why you shouldn't memorize it? It's on the formula sheet. All right? Check your announcements. It's right there. All right? These properties are really just versions of the properties of exponents we have discussed in chapter 6, whatever. For example, the first property really says that the number represented by the square root of a times square root of b should be the non-negative solution to x squared is equal to a times b. Is this true since the square root of a squared is equal to a and the square root of b squared is equal to b? Then also square root of a times square root of b squared is equal to square root of a squared times square root of b squared, which is equal to a times b by the property of exponents. So the square root of a times square root of b really is a solution to x squared is equal to a times b, and the equality of property S1 is valid. We now show through a series of examples how these properties can help us to simplify square roots. All right. Blah, blah, blah. Let's do some examples. Keep it simple. All right. Woo. It's a hard example right here. Bless you. See, I gotta stop giving y'all the easy examples for homework and do them joints up here instead of doing the hard questions up here, man. It's not that easy. We can. Let me finish this though, and then we can do that. All right. Let's look at A. I have the square root of 12. All right. What is a perfect square that goes into 12?
3. Oh,
4,
four.
right? So square root of 12 can be written as what? Square root 4 times square root 3. And then help me out. What is the square root of 4?
2.
2. So this is my final answer. 2 square root 3. And I'm done. That's it. Go ahead. All right.
It can be split into simplified, yes.
Right. So what is a perfect square that goes into 72? I hope y'all know because I don't know.
1 word can be multiplied for
4 times what? Is it 9? I don't even know. It's 9? 9 times what is 72?
9 times 9 is 81, so it has to be 8 or something, I don't know. 8 times 8
Let me see.
is
9.
64. So it might be closer than 72.
It is that. 8 times 9, right?
Okay.
So the largest perfect square that goes into 72 is going to be square root 9 times square root 8, right? Okay. What's the square root of 9? Huh?
3.
3, right? So I have 3 square root 8. All right, let's try that again. What's the largest perfect square that goes into 8? What's the largest perfect square that goes into 8?
2.
Not 2. 4, right? So this is going to get rewritten as 3 square root 4 times square root 2. What's the square root of 4 again? 2, right? So this is 3 times 2 square root 2. Final answer, this is going to be 6 square root 2. So what did we learn there, right? We don't have to know what the perfect square is, like the big perfect square. We can find little perfect squares along the way, and then we'll get down to the final answer, right? The shortcut for this would have been square root 36 times square root 2, which becomes 6 square root 2. It's okay if you didn't see 36, right? You saw 9. That was fine, right? If it was me, I probably would have done the 4, keep it simple until I figure it out in the end, you know? That's okay. All right. I'm gonna just box it because it's the same answer, right? All right. Now I know C is gonna be mad simple, right? This is square root 75. What's the largest perfect square that goes into 75? Exactly, right? So this is square root 25 times square root, that's what I'm talking about. What's the square root of 25?
5.
That's what I'm talking about. 5 square root 3. That's my answer. Questions on this? You good?
7,000.
You can. All right, so 1,000 or 100?
0.
So I would separate that as 27 times 1,000. And then break down square root 27, break down square root 1,000. You know?
Just give me 1 minute and I.
Yeah, copy. Go ahead. Go ahead. You got time. Do it on paper, right? So 27,000 is the same as 27 times 1,000, right? So break down square root of 27, right? 3 root 3. And then what's square root of 1,000?
Yeah, that's like the highest.
What about 100? I might be wrong about that. Let me check. Ooh, that's 10,000. Nope. That's all right. You said 25 times 40? Go with that. And then break that down further. So that'll be 5 times square root of 40. Be 4 times 10. Square root of 4 is 2. Which is 10. So 10 square root 10. Now those two numbers that you found, the 3 square root 3 and the 2 square root 10, multiply those together. That's your answer. All right. We're gonna get to that. We didn't get to that yet. 10. Yeah, we didn't get to that yet, but we're gonna get to that right now. Oh, 1 second.
It's like square. Yeah, what do you do that?
Multiply them together.
Square.
If the multiplication is right, I didn't do it in my head. Okay. All right, let's try something else. This should be fun. So I told y'all it's illegal for me to have radicals in my denominator, right? So for A, this is going to be simplified down to what? This is square root 3 over the square root of 4. Help me out. What's the square root of 4? That's what I'm talking about. So here's my final answer. Square root 3 over 2. I'm done. Questions on this? All right. Let's try the next one. I have square root 50 over the square root of 9. What's the square root of 50? All right, square root 25 times square root 2. Very good. Over, what's the square root of 9, right? So what's square root of 25? This is 5. Square root 2 over, what's square root of 9?
3.
That's what I'm talking about. Done. Any questions on this? Huh?
As I'm looking at my notebook right now, I'm using myself over there.
Yeah. Oh, you mean with the simplifying thing?
The last one is the what? Square 75 is the
Or that one finding the largest perfect square? Yeah. So let me share with y'all the trick to that real quick, right? So you want to go through your perfect square numbers, right? So 1 times 1, 1, 2 times 2, 4, 3 times 3, 9, right? So you know what your perfect squares are, right? You have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, etc., right? Whatever number you guys have there, square root of whatever, find the next smallest number from the perfect square list, then and divide it. Whichever one can go into it evenly, that's the perfect square. For example, right? I had square root 72, right? So we know that 9 times 9 is 81. 81 bigger than 72, so it can't be that, right? But 8 times 8 is 64. 64 smaller than 72. So what would I do? I would do 72 divided by 64. Now, does 64 going to 72 evenly? So I know that that ain't it, right? What's the next one after that? This is 8. So now 7, right? How about 49? Does 49 go into 72 evenly? No, I don't. Yeah. I'm right. I'm showing you an easier way to go through it, right? I'm telling you, go through your perfect square list, right? So you got 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, etc. Right? 4, 5, 6. Now, for this case, hold on. 25, 36, 49, 64, right? And then let me just do one more. 9 squared is 81, right? 81 is bigger than 72. So I know that 81 can't go into 72. Start with the first perfect square that's smaller than what's ever under the radical. 64 is smaller than 72. So that's why I'm gonna divide by 64, right? But when I divide by it, it doesn't go in evenly. When I say evenly, that means like when I divide it, I'm gonna get a whole number out, you know? I'm gonna get some decimal out of this. So that's why 64 don't work, right? How about 49? When I divide 72 by 49, I'm gonna get a decimal number out there. That don't work. But when I divide it by 76 now, I mean by 36, excuse me, 72 divided by 36, that gives me 2. So boom, I already know this is going to be what? Square root 36 times square root of 2, 6 square root 2. That's the easy way to do it. Just go through that list in reverse, you know? All right, give me 2 more examples. Like I just got 2 more examples to show y'all, then we could start taking some homework questions, all right? So in the previous example, we were lucky to encounter fractions in the radicand whose denominators were perfect squares. The next example illustrates how to simplify when this is not the case. It involves a technique known as rationalizing the denominator, right? Here, the word rationalize implies making an irrational number rational by multiplying by the appropriate number. All right, check this out, check this out, check this out. This is going to be fire right here, right? You see for this one? You already know this is going to be what? Square root 1 over the square root of 2. What's the square root of 1? So this is 1 over the square root of 2. But I'm telling you, it's illegal to have the radicals in the denominator, right? So how do I get rid of that square root of 2? You're going to multiply it by the square root of 2. But what you do to the bottom, you got to do to the top. And how do we multiply fractions? All right? Straight across. So 1 times square root 2 is just square root 2. And then square root of 2 times square root of 2 is the square root of 4, which is perfect. And that's it. Right? So when you multiply 2 radicals that are the same, right? The square root jumps out and it's just the inside number. All right? Let's try it again. I have square root 3 over square root 8. What's the largest perfect square that goes into square root 8?
4.
That's what I'm talking about, right? So I have square root 3 over square root 4 times square root 2. What's the square root of 4 again?
2.
That's what I'm talking about. So I have square root 3 over 2 square root 2. Now I have to get rid of that radical on the denominator, right? So what am I going to multiply that by? I have to get rid of the radical in the denominator. So what am I going to multiply it by to get rid of the radical?
Well,
But what am I going to multiply it by? By what?
3.
Mhm.
2 times 2.
Mhm. The denominator, right? All right. What did I do in the first question? What did I multiply this by?
Denominator.
Right. I just took the denominator and I multiplied it there. What I did to the bottom, I did to the top. Do the same thing here. So what am I going to multiply this by?
2 times 3.
No.
3 times 2.
What is it? Square root 2. Whatever you see here, just multiply it there. And whatever you do to the bottom, you do to the top. That's it. That's it. Then you just multiply straight across. Square root 3 times square root 2 is square root. That's what I'm talking about. All right. What is 2 times square root 2 times square root 2? No. 2 times square root 2 times square root 2 is what? It is 4. Very good. All right. I know he did that in his head, but for everybody else, this was like this. 2 square root 2 times square root 2, right? So when I multiply these together, this just simply becomes 2 times 2, which is 4, right? The two radicals are the same, right? So it just simplifies down to 2, and then 2 times 2. All right? Questions on this? They'll be there for the homework, don't worry. Huh? Next tutoring tonight. I'm going over there right now. All right, just let me just do this last question real quick, and then we'll wrap it up at that. Because just like y'all, I got to run too. All right. All right, I'm gonna go a little bit fast with this because time is against us. We only got a couple minutes. All right. What up? All right, there we go. All right. So real quick for A, I have x squared is equal to 16. How do I solve for x? Tell me what to do. No problem. No problem. Gotcha. Square root, right? I'm going to square root both sides. What I do to one side, do to the other. Right? So now I have x is equal to, what's my answers?
Negative 16.
Negative 4. And what else? That's what I'm talking about. Right?
Yeah, sure.
This is 2. All right, how about this last one? I have x squared is equal to 98. I know you got this one, man. Tell me how to do this. I know you got this real quick. So what I got to do, I got to square root both sides, right? So now I got x is equal to plus or minus. Come on, what is it? I know you got this, man.
Can I go?
Yeah, you could go. Did you sign? Did you sign? Yeah. I'll give you a couple of seconds because the time is running. Nah. All right, I see. Did you sign? You guys signed already? Sign. All right, that's time. Look, square root 49 times square root 2, right? And then what's the square root of 49? That's what I'm talking about, right? So plus or minus 7 square root 2. If this was web work, you would say what? Negative 7 square root 2 and 7 square root 2.
Cause I
Alright.
told you I ain't been to school in a minute, so this is.
I got you. I got you. Yo, can I take this down? Let's see, man. Can I take this down real quick?
When you square root and.
All right, take a picture real quick.
Come out to like.
Yeah.
Same as like number like square root of 81, so
Yeah.
89.
Right.
Because it's.
It's 9 times 9. Yeah.
That's what I realized.
Yeah.
Remember.
Yeah.
You bringing out the 49 square
Yeah.
plus 2 square.
Yeah.
It's like.
But do the perfect squares in reverse though. Right. So remember I was saying, like, 10 times 10 is, all right. So you know that 100 can't go into 98. So what's the next perfect square after that? Be 81. 81 don't divide into 98 evenly, right? So then now you're gonna check out 49 and then boom. Yeah, I got you. All right, man. Yeah. Well, not 64, then that one, right? Yeah. All right, all right, see you. You signed me?
Yeah.
All right, here. All right, I'm gonna take this down, all right?